Hi all, welcome back to my channel. In the previous video, we learned about what is time complexity and why it helps us to avoid time limit exceeded. Today, let's look at the actual types of time complexities you will see in coding with some simple examples. By the end of this video, you will clearly know which algorithms are fast, which are slow, and which ones you should avoid for larger inputs. Let's get started. The first one we have is big of 1, that is nothing but a constant time. This is the fastest complexity we have. Big of 1 means the time taken does not change with the input size. Whether the input is 10,000 or 1 million, it takes the same amount of time. In graphical representation, we can just say it as a horizontal line as it is independent of input size. So now coming to the simple example, let's say we have an array of elements size 5. Now I have to print an element which is at the index 2. It just takes a constant time, or we can set a fixed amount of time. And also if array size is 1000 or 10,000, I have to access an element at particular index, it takes a fixed amount of time. So whenever your logic does a constant or fixed amount of work, it is big of 1 complexity. And the second one we have is big of n, nothing but linear time. Here the time increases directly with the input size. So for example, if you have an input size of 10, your complexity would be big of 10. So if n doubles, the time doubles. And in terms of graphical representation, we can just say it like this, as it's directly proportional to the input size n. Now in simple example, we can say if you have to print all the numbers from 0 to n, let us say some n might be 100 or 10, we have to iterate from 0 to that particular number. So the line of code which is in the for loop will iterate based on the input size n. So if n is 10, it iterates 10 times. If n is 100, it iterates for 100 times. It's directly proportional to the input size n. So this is example for the big of n. Now the third one we have is big of n square, nothing but a quadratic time, where here this happens when you have two nested loops. That's a golden rule where we can remember easily. So the graphical representation would be here will be a like raising curve or increasing curve. For example, now we can say this as if n equals to 10, it runs about 100 operations. For 1000, it runs for 10 power 6 operations. So big of n square basically leads to TLE, that is time limit exceeded for larger inputs. And in simple examples, we can say like if we have an array of size some 5 or 6, now I have elements like this 1 2 3 4 1. Now I have to find whether this array contains a duplicate element, or exactly I have to find what is a duplicate element. The brute force approach would be like I will iterate all the elements from each index, and then I'll also have a nested for loop where it will iterates from the immediate next element. So that means basically we having two for loops, whereas the first for loop will iterate for n times and the second for loop will also iterate at max for n times. So this is how we calculate as big of n square. So we have to try to avoid this big of n square time complexity algorithm basically when we have a larger input size like say 10 power 5. And the fourth one we have is big of log n, that is logarithmic time. So this is one of the most efficient time complexities. So here the basic rule is instead of checking each and every element, we keep cutting the search space in half. So the most popular example for this is a binary search, where here we'll keep on searching the half of the elements each and every time. So for example, if we have an array of size 9, now I have to find a particular element here. So first, based on some criteria or condition, if that was met, I will make this my array to be half of it. So for example, my search array became 1 2 3 4 5 now from element 9. Now again, based on some condition, I will make it to half and it become 4 or 4 comma 5. Now in this, my element could be there, whatever I am going to search. So instead of searching each and every element of size n, that is big of n would be I have to search for 9 times. I just found this element in just 3 steps. So this time we'll call it as big of log n. So only rule to remember the time complexity log n is like when you are making the input size half each and every time you are making it half to search particular element or to make any operation, we'll call it as a big of log n. So the graphical representation for big of log n time complexity would be like this, as it grows very slowly when the input size increases. That is why it is termed to be as one of the best time complexity we have. And the last one we have is big of n log n, that is linearithmic time. We could say the merge sort and heap sort are like most popular example for this time complexity. It is faster than big of n square but slightly slower than big of n. Here to explain in one line we can say that this array is divided log n times, similarly how we have seen for the previous one, but each log n times will be performing some iteration again, which takes again complexity n times. So that is how we got n into log n times. So this merge sort and heap sort will be covering in upcoming videos. So these are all about the basic time complexities we have, which will be using more in coding in basic DSA as well. So if you have to remember all the time complexities order, which is most important for solving the problems and deciding whether your algorithm takes more time or less time or the best one or the worst one, we have to remember this order. The first one we have is big of 1, which is the fastest algorithm we have, and the last one we have big of n factorial, which takes more time to execute it. That means we can say the algorithm with big of n factorial would take more time to execute it. So this is all about this video. To have a conclusion, we can say that understanding these complexities help you choose the right approach for coding problems. So in the next video we will solve real problems using these complexities, so you will know how to apply them in interviews and competitive programming. So thanks for watching. If this really helped you, don't forget to like, share and subscribe. See you in the next video. Thank you.